Yeah, well, thank you very much, Mason. And I have been coming to these peer meetings for over 20 years, and they keep getting better and better. So congratulations to Peer and its whole community. Charlie, that was an interesting video. Remember, I was with you on that trip. I was sitting there in the middle of a row watching those chandeliers shake, thinking, well, 3 weeks ago, a magnitude 9 earthquake happened. It's probably not going to happen again, and those chandeliers didn't fall yet. So, anyway, so last speaker of the day of a 2-day workshop, I better be good or I better be quick. All I can say is I've been pulling slides out of my slide deck all day. So I would like to challenge us to think beyond, think of performance-based, but to think beyond the performance of buildings or infrastructure is how it informs disaster recovery. We talk about resilience. Well, what's resilience? A lot of it's recovering from the disaster. So what we do to help inform that. The word high fidelity is probably not quite right. I think about these simulations as being multi-fidelity types of models that we could put in. Also being high resolution, I'll show what that means. And probably another word should be in there, also multidisciplinary, to really inform these recovery processes. I think, Charlie, you said the past is a prologue for the future. If you go back 20 years, it was Bill Holmes who put together this slide early in Peer, contrasting on the right side there kind of the HASIS type methodologies and the so-called death dollars and downtime. We didn't invent them, they were there in HASIS at the time. On the left side was the very detailed building specific, at the time FEMA 273 with the immediate occupancy life safety. And in between was building performance ratings, the so-called PML, which is looking at dollars. And Bill's point was really what Peer is after is kind of a convergence of these things, that is trying to bring them together under one performance engineering, performance framework, if you will. And I think we successfully did that to a degree. We certainly brought the performance engine into the building model. And of course, folks are familiar with our triple integral equation and breaking down this process here. This maps over nicely to looking at an individual facility, looking also at a bridge or another thing like that is going from the ground motion through the damage to the losses and the consequence. And in concept, it carries over to distributed frameworks as well. And in fact, early in the days, it was work by Ann Karamidjan looking at transportation networks, looking at that. But I think we still have a ways to go to kind of take this methodology to these regional simulations that can, I think, really inform disaster recovery. And at the time, again, the FEMA 273 was our kind of performance state of the art, if you will, for evaluating buildings. And if you think of where we've brought that through today, through Peer's research and the subsequent efforts, looking very quantitatively at the losses as a continuum, casualty rates in buildings, and the downtime metrics. And of course, that was then pulled into FEMA P58. There's now software out, and it's becoming pretty routine for some engineering design offices to be applying this to buildings and advising owners on looking at alternate structural types and so forth, how they could get higher performance buildings and what would be the value in terms of looking at the reduced, at least, dollar losses. I think that the repair time and then further the downtime are still things we're still grappling with. I'll talk a little more about that. About the same time, actually, that about 10 years ago that P58 was coming out at kind of the end of the first 10 years of Peer, when we had this technology and this framework had matured. San Francisco was underway with the so-called Resilient City Project from the Spur, looking at championed by really Chris Poland, but a number of urban planners, city planners and so forth coming together, and really looking seriously at the city. That is to say, if a big earthquake happens in San Francisco, what's going to happen to buildings and other infrastructure, and how does that affect the services in the city, and what's going to be the reality versus what's going to be the target that would make the city resilient. And in fact, San Francisco and it's LA, and now through NIST, this whole notion of resilience and community planning has marched forward. And the question is, how can our performance-based tools really quantify things and impact this? So you could think of on the left side kind of HASIS type technologies, which is looking at pretty simplified models, census tract inventories of buildings, and simplified hazard models, and going to a more simulation-based one. This is a slide Professor Hori from the University of Tokyo put this together, Also, Professor Xinjin Liu, who's here from Tsinghua University, does some of these models as well. And of course, Dave McCallum talked about, starting from the earth science side, the great advancements made there. How do we carry that forward all the way, looking at not just earthquakes, but other hazards, but also the effect on our infrastructure, the effect of the systems, the piping systems, transportation, but also going forward to the economic systems. So in the Sim Center, Sanjay Govinjay had a short talk yesterday where he talked about a number of the tools we're developing. A key feature of that is these so-called workflows. These puzzle pieces, this is really the brainchild of Frank McKenna, who's here in the audience, the software architect for the Sim Center, together with Steve Mahan, who put the proposal together for this with Frank. But thinking of all the computational tools we have, starting at how we define assets, the inventories and what sort of technologies to build inventories, how we describe the hazards. It could be with ground motion prediction equation. Jack Baker talked about using some of those yesterdays. Dave McCallum just talked about earthquake simulations. You could think of tsunami simulations and so forth. And then what's the effect of those hazards on the built environment? What are the damage and the losses? So it's really putting together a computational framework for the, if you will, the peer framework, what we do for an individual facility. But the idea by taking these models and putting them together so you can plug and play conveniently, so it's not a huge research effort to do so, that you can start to do regional simulations with the whole community, just as the triple integral equation was a very unifying concept for peer. In other words, people could see where their research plugged into it. So similarly, as we take models and make them computational, we have data sets to see where they plug into this kind of computational flow. Keep in mind too, we want to kind of characterize the uncertainties throughout this whole process, as Dave described, as you could start to do these exascale computing, you could do these over and over again to capture the uncertainties throughout not just the ground motions, but the whole loss estimation and recovery process. One of the testbed studies we did was actually using some of the Art Rogers, the simulated ground motions, taking 1.8 million buildings. These were open seas models that were put together. Along the lines of what Dave described, we didn't have it on the, we're actually using the Stampede computers through DesignSafe. Had to infer something about, we knew of the general population of buildings in the Bay Area, infer something about structural systems, so models to do those inferences, doing FEMA P58 type loss assessments, and getting then estimates of what would be red tag buildings, what would be the losses from those. This is actually the same scenario that was recently came out as the Haywired about 2018. And I contrast here the results that we have, SimCenter on the left side and the Haywired. Haywired is using kind of HAZUS technologies where the building inventories are census block. You notice when I first saw our picture on the left, I wondered why it was so striated like that. And of course, there's no building sitting on the Hayward Fault. So the damage there really reflects, firstly, the population density of buildings, and then how severely they're being damaged. But this is a key part of these kind of tools we're going after now, this kind of high resolution that is building by building, parcel level, component by component. And you see pictures like this if we zoom in a little bit further. And so if we could do these simulations, then the question is, what information can we start to, how do we use this information? Who's going to be interested? So when you start to then talk to urban planners or to people in the cities that think about vulnerable populations, instead of a census block of one part of a city, you could imagine going block by block. Are there vulnerable masonry structures, vulnerable cripple wall apartments, soft story structures, and to really get high resolution? And then you could start to really affect not just engineering the buildings or not engineering the retrofits of buildings, but engineering the cities, the urban planning for land use, retrofit policies, and so forth. So that's sort of the vision of where we want to take this. One of the tools that we have, this is, we've developed, Adam in the audience had kind of as a postdoc behind this, is a tool called Pelican. Those of you that are familiar with, say, the FEMA P58 methodology for buildings, this high resolution performance assessment for an individual building, this sort of toolbox is built around that framework. But as you see in this graphic here, we're trying to build it out beyond whereas FEMA P58 does earthquakes and buildings. We're trying to build that out to look at other kinds of infrastructure, looking at kind of that same detailed methodology, how you'd apply it to pipelines or bridges or so forth, and then to look at, as part of NERI, to look at other hazards, in particular hurricane. But this Pelican, this is an open source, multi-fidelity, that is, we could also build into this tools that are based on, say, the current tools that are in HAZUS, because, for example, looking at damage to pipelines, we don't have, researchers are developing high fidelity, but for the time being, plugging in the simplified tools there. And sometimes you want to mix and match. There's certain parts of a city or region where you really want the high resolution, and you build the detailed inventory. There's others where you don't need that as much. So having this trade-off, being able to do regional simulations with certain buildings or infrastructures being built with kind of very detailed high fidelity models and some with the more efficient models. So just a few examples you saw in Holland introduced, and if those of you that went to the session from the CEA, looking at one of the peer projects is the benefits of retrofitting cripple wall houses. Well, why are we doing this research? Well, this is a plot showing some loss data from Northridge and other buildings, looking at the damage ratio on the vertical axis, the spectral acceleration on the horizontal, and there's the data. And by the way, there's a lot of data points up at 1 and a lot down at 0. But if you take the average, you get that nice red curve in the middle, which is pretty close to the HAZUS average. So on average, these loss assessment tools do wonderful. And so if you're interested in the aggregate loss, these tools are adequate. But what if you're interested in what happens to individual neighborhoods, or what's the benefit of a cripple wall retrofit? So this is really the essence of that CEA-funded project for peer, looking at taking a number of different house archetypes, different siding types, stucco, wood frame, 1-story, 2-story, different kinds of interior partitions and so forth, and really looking at the different loss curves, and if you retrofit the house, how the losses reduce. For the CEA, they're focused on two things. One, thinking of working with the insurance industry, trying to give incentives through insurance for retrofitting houses, but also trying to benefit the folks of California. But you can imagine there could be other folks with this technology that if we have this and you build it into regional simulations, if you could understand the parts of town where you have a lot of old houses, to understand in the community of Oakland or San Francisco, LA, where do you have these houses where the damage might be? I mentioned to Craig Davis, was formerly with the California LA Water and Power, in the fires a couple years ago, what does LA think about the water system? He says, well, I'm worried about these places downtown with a lot of old houses where our water system goes through some soil that's not so good, we're gonna have a lot of breaks. And I said, well, those houses are probably cripple wall houses, and they have gas pipelines coming into them. So you can imagine this cascading effect you could start to pick up if you build these into these regional models. Brian Strong mentioned this San Francisco tall building, one of their many programs they've looked at. We worked on building an inventory of some of the tall buildings, understanding the different occupancies, also the different structural types, when they were built, foundation types. That's an interesting subject in San Francisco these days. But this just shows an inventory of the number of tall buildings built through the different decades. The reddish ones are concrete, the greenish ones are steel frame, moment frames, the bluish ones are steel brace frames. But then if you look at kind of events in history, San Fernando, you notice there weren't too many tall, at least over 240 feet, concrete buildings in that inventory. But then if you look at the Northridge earthquake, which is where, of course, we got alarmed at the performance of steel frame buildings, you see most of the tall steel frame buildings were built prior to Northridge. There's also the advent of the performance-based tools, which buildings at that point and beyond, we kind of have more faith in, using better methods of analysis. So one thing that came out of this was identifying the number of these tall pre-Northridge steel moment frames and the clustering them in downtown. Brian Strong mentioned this in his talk yesterday. Well, since Northridge, that was now 25 years ago, we've built better computer models. In research, we've continued to work away at fracture mechanics type models to simulate, say, the connection failures. So we could go back and look at some of these buildings now and think, can we start to predict this damage better than we could 25 years ago? And I'd like to think we can. But then also to look at some documents like FEMA 3552, this was developed by the SAC project, that looked at evaluating and tagging and looking at the safety. It was kind of very qualitative, had quantitative numbers, but based on judgments that were in there. And I think a question we have to ask today, if the Northridge earthquake happened and we got the connection damage of the type that's shown there, can the building be occupied while we repair it? Or is this building so damaged it's not occupied, but it might be a danger to its neighbors? So I think this is an important challenge. Is it safe to occupy during repair? because that's a key part of this reoccupancy, but also looking at the neighboring buildings downtown. And then it also gets into this whole concept of functional recovery, which is an emphasis now in the NEHRP reauthorization. And this is important because suppose in a building like that, you estimate it's going to take 2 months to fix the repairs that you saw there. Well, if you decide the building's not safe to occupy, you have these impeding factors before you could get those repairs underway that might extend that total repair time to 9 months. And if you cannot be in the building over those 9 months, it's a much different story than if you could be in the building while it's repaired. So I think these are kind of another hurdle or another challenge we could face, but we have the technologies to do it, so we could start to apply them to problems of this sort to look again at recovery of communities. You know, Jack Baker showed some of this work yesterday, and Ann Holsey, our student, had a paper on it, and Charlie, you mentioned cordons a minute ago. You know, but the idea of looking at clusters of tall buildings, this shows a little mapping of San Francisco, many of them around. If there are cordons around one or more buildings, what it does to your immediate neighbors in terms of slowing down the recovery of not just your building, but the buildings in the shadow of that tall building, what it does for emergency response, recovery or reconstruction, and taking it further, the whole downtown economy. And that's people, Brian Strong and people in the city of San Francisco. Ultimately, it is their livelihoods and your community we want to understand better. You could take those same concepts carried over to any sort of other system. So distributed transportation systems, having again, mix of low and high fidelity model of bridges. You could look at, this is a picture from some work Jack Baker did. You know, when we think of a bridge, you could identify it on a map, but if there's a bridge with a road under it that has another bridge nearby, can our models have the resolution to understand the conflicting effects? In fact, I was talking to Ian Buckle about a bridge that has a refinery underneath it. so to build those things into our models. I'd be remiss if I didn't remember my geotechnical friends here and pull up Ahmed Elgamal. I'm not sure if Ahmed is still here. The old Humboldt Bay Bridge, one of our test beds from the early pier days. I'm always humbled by this to think, you know, as a structural engineer, that there's a lot of soil underneath that bridge to really understand. That's part of this picture as well. And it interfaces, Dave, with what you were showing with the earth scientist simulations. There's that geotechnical layer we need to build into these models. Of course, there's more work to be done. I was reminded, Ellen Rathje, some of you might have seen her Joyner lecture from last year. It was looking at bridging the gap between a geotechnical engineer's view of modeling of landslides and an earth scientist's view, and really looking at multi-fidelity models. The engineers taking a higher fidelity model compared to what's looked regionally from the earth scientists. So you could imagine these regional models can similarly build in. The fidelity of models is not just buildings and bridges in the geotech, but it could be looking at things like landslides and their effect on roads and other things like that. So mixing and matching, this kind of concept carries over to any of these. A couple last slides just to remember, in all of this simulation, going back, those of us that remember the beginning of the NEES program some years ago, it was that simulation was going to replace experiments. Well, nothing is farther from the truth. As we come up with these more grandiose analyses that we need, it just beckons for having more tests. This is an interesting new soil box on the left being built up at the University of Nevada, Reno, but also field exploration to know the geotechnical conditions, structural conditions and so forth, and to do more testing and validation. One of the questions we get asked is, well, how are you going to validate these regional models? The reality is we're going to have to wait a while till we get enough events to validate them, but in the meantime, putting up benchmark exercises where I could run a model, or we put it up there, we run an analysis, and someone could say, well, you know, if I plug in my ground motion model, I get sort of a different answer. We could start to benchmark them against each other. In fact, that's what the earth scientists on the earthquake simulations are doing, exactly that, to kind of, if you will, I don't know if the word's validate, but gain confidence in their earthquake simulations. So I'd like to just sort of end here. This is a slide that Brian Strong showed yesterday. I actually dug it up this morning, this report, this Hazards and Climate Resilience Plan with the City of San Francisco just put together. It's really quite amazing. This is a city-led effort with all their departments. They look at the risk landscape, what's in the city of San Francisco, both the buildings and the infrastructure, but the people, the economics. They go through a whole list of hazards. This is a few that are just more germane to what we're talking about here today. And then they talk about risk consequences, the capabilities that the city has to address them in the strategy. And I think this is a wonderful report. When you look at risk consequences, it's pretty qualitative. You know, they look at liquefaction areas and they look at the number of buildings they have there, and they kind of say, well, bad things could happen, but that's about as far as it goes. And then when they think about strategies, again, how are they going to prepare? But I think these are opportunities that as researchers and working with design or engineering professionals, urban planning professionals, to make those connections more quantitative and really help cities like San Francisco, states and countries, you know, better prepare and really, again, like not just engineer the buildings, but to engineer the cities and policies and so forth. So with that, thank you for your attention.